All right, so we've talked about vector spaces, and we've been kind of going back and forth between some of these image examples to give us a sense of maybe some motivation behind why we want to do some of these things. So thinking about our image question, let's ask the question, what images could we create with the linear combinations of a given set of images? So we say that an image Z is in the span of a set of images if Z can be written as the linear combination of the images that we have. So we say Z is an element of the span of I, where I is the images we're talking about. We also say that the span of I is the set of all linear combinations of the images in I. So this is going to be kind of our way of talking about these definitions. It'll be kind of helpful to kind of know the difference between the different ways we're talking about span as we go forward. So as an example, when we looked at Lab 2, image 3 from Lab 2 was in the span of the images A, B, and C because you could take image 3 and write it as some A times image A plus some B times image B plus some C times image C. But image 4 is not in the span of A, B, and C because we couldn't write it as a linear combination of those images. So we would say yes, that image 3 is in the span of images A, B, and C. Now, something we'll get to eventually is subspaces. Because the span of those images is determined by the same operation as closure of vectors, vector spaces, we might ask if the span is a vector space. Indeed it is, and it's also a subset of the set of all possible images of the same geometry. So we're going to say that W is a subspace of V if the non-empty and if it's non-empty and is closed under image addition and scalar multiplication. A little bit of notation for us. If we say that V equals the real numbers, then 3 is an element of V. So if we say X is an element of V, it means X is an element of V. So 3 is an element of the real numbers, so that would be an example of using that symbolism. I think we've seen it a couple of times in class, but I wanted to make sure it got mentioned just in case we weren't quite sure what was going on. We say that U is a subset of V using this symbol. So if U is equal to the set of all even numbers, then U is a subset of the real numbers. So even numbers are real, and so there we have a subset for us. All right, so let's get into a formal definition then for span. In this class, we're going to use the word span as both a noun and a verb, and it's going to get all sorts of confusing, so hang on. We're going to start with the definition of span as a noun. So let V be a vector space, and let X, which is the set of V1 through Vn, which is all a subset of this V, be a set that we're working with. So here we're saying that all of these vectors are part of this bigger vector space, but we're not going to use all the vectors from V. We're only going to use some finite subset of them. Then the span of the set X is the set of all linear combinations of the elements of X. That is, the span of X is the span of those vectors V1 through Vn, which is going to be equal to the set of all alpha 1 V1 plus alpha 2 V2 all the way through summing up to alpha n Vn, where all the alpha 1 through alpha n's are scalars. Now there's some reasons we're going to care about span. It allows us to encode vector spaces compactly into some building blocks. It helps us represent the set of possible outputs of a vector space. It helps us determine if subsets of vectors give us the same set of outputs, and it'll help us determine if a vector is in a vector space. So what we're going to do is we're going to walk through the process of trying to determine if a vector is in the span of some other vectors. So we're going to let V1 be equal to 3x plus 4, V2 equal 2x plus 1, V3 equal x squared plus 2, and V4 equal x squared. We want to know if V1 is in the span of V2, V3, and V4. In other words, the question we're asking is V1 equal to some alpha 1 times V2, we were going to call it alpha 2 just for posterity's sake. So alpha 2 times V2 plus alpha 3 times V3 plus alpha 4 times V4. So we want to know, can we find alphas that let us combine V2, V3, and V4 to get V1? So let's write this out a little more formally. Instead of using these placeholders, can we say that 3x plus 4 is equal to alpha 2 times 2x plus 1 plus alpha 3 times x squared plus 2 plus alpha 4 times x squared? So when we're looking at polynomials, what we're going to want to do is we're going to want to compare the coefficients of those polynomials. And so what I mean by that is we're treating x as the variable here. So I want to make a little bit of a note here. X is not our variable. Alpha 2, alpha 3, and alpha 4 are. So those are the things we want to solve for. And so when we're looking at trying to figure out and solve for certain things, when we set up our system of equations, we're going to be trying to solve for alpha 2, alpha 3, and alpha 4. So then here, let's distribute this through. We get 2 alpha 2x plus alpha 2 plus alpha 3x squared plus 2 alpha 3 plus alpha 4x squared. Now, on the other side, we still have 3x plus 4, but notice that we have x squareds over here. So we seem to be dealing with something that has degree at most 2. So because of that, we should have some sort of x squared component on the left to compare this to as well. However, there wasn't an x squared here before, so we're going to say it's 0x squared. So notice that 3x plus 4 is the same as 0x squared plus 3x plus 4. So now, we said we wanted to compare the coefficients. So what we mean is that we want to compare what's in front of the x squareds, what's in front of the x's, and what's our constant portion. So let's rewrite this where we combine our like terms. So we should get, if we look at things that have x squareds, we will get alpha 3 plus alpha 4 x squared. If we look at things with x's in front of them, we'll get 2 alpha 2 x. And if we look at things that don't have an x attached to them, we will get plus alpha 2 plus 2 alpha 3. And that has to be equal to 0x squared plus 3x plus 4. Okay, so if we want to go ahead and create a system of equations out of this, we're going to compare the things in front of the x squareds, the things in front of the x's, and the things that are just constant portions. So let's create a system of equations then. So here we say that alpha 3 plus alpha 4 is going to have to be equal to 0. We'll also say that 2 alpha 2 equals 3 by comparing the things in front of the x. And then when we're comparing things that are just the constant portion, we'll say that alpha 2 plus 2 alpha 3 equals 4. So the next thing we're going to do is turn this into a matrix. Now remember, the rows of your matrix are going to be your equations, and the columns are going to represent the coefficients of your variables. So we have here an alpha 2 column, an alpha 3 column, and an alpha 4 column. So let's go ahead and read this first equation. We don't have any alpha 2s, we have 1 alpha 3, we have 1 alpha 4, and it equals 0. Our next equation, we have 2 alpha 2, no alpha 3, no alpha 4, and it equals 3. And then for our last equation, we have 1 alpha 2 plus 2 alpha 3, no alpha 4s, equals 4. Now when we take and put this into reduced row echelon form, which you can do either by hand or with Octave Online or with your calculator, we'll get 1, 0, 0, 1.5, 0, 1, 0, 1.25, and 0, 0, 1, negative 1.25. So this tells us then, this is why we like reduced row echelon form, that alpha 2 equals 1.5, alpha 3 equals 1.25, and alpha 4 equals negative 1.25. So what we're saying then is 3x plus 4 equals 1.5 times 2x plus 1 plus 1.25 times x squared plus 2 minus 1.25 times x squared. So we can verify this just to double check. If we multiply this 1.5 through, we'll get 3x plus 1.5 plus 1.25 x squared plus 2.5 minus 1.25 x squared. And so when we check, we have that our 1.25 x squared and negative 1.25 x squared will cancel. We'll see that if we look at just the 3x, that's all on its own. And if we look at 1.5 plus 2.5, we'll end up getting 4. So we get 3x plus 4, which checks out. So because we were able to found at least one solution for alpha 2, alpha 3, and alpha 4, V1 is an element of the span of V2, V3, and V4. Okay, great. So that's how we find that something is in the span of some other things. We want to find the span of two polynomials, x and 1 in P1, denoted as a span of P1. So here, if we want to go ahead and write the span of x and 1, this is us saying that we have the set of all Cx plus D such that C and D are in the real numbers. Well, this is our definition for P1. We use different letters, C and D, but the idea is we're combining some sort of x and we're combining some sort of constant term. We also want to look at the span of x and 2. So this is going to be fx plus 2g, where f and g are real numbers. Well, this is also taking some sort of x component and some sort of constant component and putting them together. This is also going to be P1. But notice that if we looked at something like x plus 3, it's in the span of x and 1, but it's also in the span of x and 2. Now, notice that we have to obtain that in different ways. So how do I know this? So 1. How do I know that x plus 3 is in the span of this? Well, I know that if I take x plus 3 and I make it equal to some ax plus b times 1, then what that tells me, by the way of looking at the coefficients, we can think of this as being a 1 here, is that a equals 1 and b equals 3. So because I was able to find some sort of solution, x plus 3 is in the span of x and 1. If I wanted to look and determine if x plus 3 was in the span of x and 2, what I'd be looking at is I'd say that x plus 3 equals ax plus b times 2. And so now I want to go ahead and compare what's in front of the x and what's the constant portion. So here we would have a system that said a equals 1 and 2b equals 3. And so if we solved this system, it's not a very hard one to solve, a equals 1 and b equals 3 halves. So because we were able to find an answer, x plus 3 is in the span of x and 2. Alright, so we're going to kind of lead this into a couple of interesting examples where we take a look at kind of a abstract but kind of fun way of thinking about this problem.